Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at Chapter 6, which is thermodynamic models of real and pure compounds, and this is a very mathematical chapter. So we are going to need a very little bit of math review now and then, and I'm going to have lots of opportunities for you to pause and try some of this on your own. First, let me remind you of what we had done in the previous video. We had developed the 4 fundamental property relations, and from those we could determine the natural variables of each of these energy functions. So du is TdS minus PdV, which means it's a function of S and V. Similarly for dH, dA, and dG, and we developed these using definitions that were for a specific process that was reversible, but now then we have something that is universally true for any change in state. Reversible, real, no matter. These are going to still be applicable. We also had developed the Maxwell relations from the second derivatives with mixed variables of those fundamental relations. And so we have these 4 definitions, I suppose you could say, but these are Maxwell relations. These partial derivatives are equal to each other because nature provides us smooth, continuous functions. We need to figure out how to use these. So let's start by looking at measurable quantities. Okay, H and U and S, oh my goodness, A, G, I don't know how to measure those, right? But it's pretty easy to measure temperature, pressure, volume, right? I have thermometers. I believe that they are telling me temperature, correct? Pressure, it's a force per unit area, so we can measure those. Volume, give me a ruler. I can handle that. We also can indirectly measure C sub P or C sub V. You may not think that you can, but I've been to many middle school and even elementary school science fairs where a child has used simple devices at home to determine the C sub P or C sub V of a substance. So these can be measured by simply, like determining how much ice is required to melt before you can heat something up, okay, for a given change in temperature. So we can indirectly measure those. But I've got no shot at measuring any of these energy functions or our entropy. Now I need one more little math review here, and this is the triple product rule. This one usually, it's covered in your Calculus 3 course. Usually it's sort of an obscure factoid that you're like, why did they tell us that? Well, this is where it's going to be useful. So a triple product rule says, it can be written 2 ways. Choose the one that makes the most sense to you. I personally like the top one that says that how x changes with y if I hold z constant times how y changes with z holding x constant times how z changes with x holding y constant, the product of those is equal to -1. Okay, and yes, this is provable, but it's a fairly lengthy proof, so I'm not going to do it here. Now, visually, I like this because, right, those, well, that color you can't see, these appear to cross out, these appear to cross out, but the key thing is that every variable is repeated one time and only one time in the path. And I forgot, the x's also cross out. So everything seems to cross out, but my path is different for each one of these, and that gives me this product of -1. Now this can also be written in this other way, which is somewhat more useful because what it says is we want to look at how x changes with y at constant path z. It is -1 over how y changes with the path z holding x constant times how z, the introduced variable, changes with x at constant path y. So either one of these is going to be perfectly valid ways of remembering this, but you do need to be able to use this in order to do some of our derivations that we're about to be looking at. Let's do this for an example problem, which is the Joule-Thomson coefficient. So the expansion valve or throttling valve that we looked at in the vapor compression refrigeration of the last chapter is an isenthalpic process. And one of the things that's very useful for that is that you can look at, if I change the pressure so much, what is going to happen to the temperature? So dT dP, how does temperature change for a given change in pressure? The path, though, of going through these expansion valves is at constant H. So therefore, what I'm really wanting to know is how T changes with pressure at constant H, dT dP at constant H. And this is defined to be the Joule-Thomson coefficient. What we want to do is see how we can use this mathematical formalism that we've developed with fundamental relations and Maxwell relations so that we can come up with a measurable way of evaluating dT dP at constant H. Now, the basic issue with dT dP at constant H is this path here, H. I don't really understand it, and it didn't show up in any of those Maxwell relations, so this doesn't look like anything that I've seen so far in this chapter. The way to eliminate this when the troublemaker is in the path is to use the triple product rule. In this case, what that tells me is that this is going to be -1 over dP, the path is H, at constant T, let's see the path, H, dt at constant P. So that's just applying the triple product rule. And I am going to do one more thing. The next step, what I want to do is rewrite this so that I move the energy to the numerator in a partial derivative. Now, dH dt at constant P is already that way, but this one here, yeah, no, I don't like that. So I am going to say that this is equal to, if I move it to the top of the fraction bar, it is the reciprocal. So this is dH dP at constant T. And then the other piece, dH dt at constant P, remains in the denominator. Okay? Now, this may not be something that you think you remember. However, dH dt at constant P, that is, by definition, C sub P. So, dH dP, don't know anything about that. But by definition, this denominator is C sub P. Okay, so I've gotten rid of the denominator, but what about that numerator? dH dP at constant T still has H in it, and I'm not too happy with H. Well, let's recall our fundamental relation. Our fundamental relation in the case of H is TdS plus VdP, and I am going to use this in order to eliminate the numerator that has the dH dP at constant T. How? Well, I'm going to simply turn this differential into a partial derivative. That is to say that instead of a d, I'm going to say dH dP at constant T is T, that d is going to become ds dP at constant T, and plus V dP dP at constant t. So I changed that differential d to a partial derivative with respect to p at constant temperature for all of those. Okay? So that's the first step of magic, but I've got one more little trick up my sleeve here that maybe some of you see coming. What is dp dp at constant t? That's just 1. So therefore, this is t ds dp at constant t plus v. Let's now substitute that into my expression that I had above. All right, well, this isn't really looking better, is it, right? Now, I've got a lot more pieces, okay? T, V, and C sub P I'm fine with, but S, we've gone from enthalpy to entropy. That's not better. But now we get to use our Maxwell relations. The Maxwell relations are all variations with the variables S, V, T, and P. So once you get all your derivative pieces that are only those variables, go browsing through the Maxwells and see if any of these seem to match. In this case, the one that matches is that negative ds dp at constant temperature is dv dt at constant pressure. Therefore, I can rewrite my expression as negative t times dv dt at constant pressure plus the volume all over c sub p. Or we can eliminate some of these redundant negative signs by multiplying this negative through. And what we are left with is that the Joule-Thomson coefficient could be calculated using this expression here. Temperature times how volume changes with temperature at constant pressure minus the volume divided by C sub P. Now this may look complex, but if I had an equation of state that related pressure, volume, and temperature, I could take that partial derivative and I would have an expression that I could calculate and I could measure everything in there. Now, I want you to practice doing some of this. So I want you to pause the video and I want you to solve this, derive the fundamental relation from these two facts I've stated here. Begin with a differential of the top line using the product rule. Substitute this in for dH. Simplify the algebra, and we find dg is equal to v dp minus s dt. Now you should be able to do any of those from any definition of an energy and one of the other fundamental relations. Next, I want you to derive a Maxwell. In this case, we want you to derive the Maxwell negative ds dp at constant t equals dv dt at constant pressure. Pause the video. In this case, we want to be working with the fundamental relation that relates pressure and temperature. G is a natural function of pressure and temperature. The fundamental relation that we just derived says that dg is equal to v dp minus s dt. And from this, we know that v is how g changes with pressure at constant temperature, and negative s is how g changes with temperature at constant pressure. And there was an equal sign in there. Okay? The final step to derive a Maxwell is to take the second derivatives of mixed variables. So I'm going to take, first, dg dp is v. So now I want to take the derivative of v with respect to t, holding pressure constant. dg dt at constant p is negative s. So the second variable or second derivative that I want is going to be the derivative of this with respect to p. So negative ds dp at constant temperature. And that is the Maxwell. This concludes this video lesson. Again, you should be able to go through and practice any of these and try some of the problems in the book, look at the examples they do in the textbook. This concludes this video lesson. Next, we'll be looking at other applications of our mathematical formalism we've developed. Thank you very much for your time.